Hello AP Chemistry and welcome to, you guessed it, more buffers. But I assure you, this is the last of the buffers, and then we'll get into titrations, which will again talk some more about buffers, but next time. So anyway, talking about buffers. So here is just some figures from your book, and I just want to talk about them to make sure that we sort of understand the concept before we solve a problem together. So here we have a figure that tells us what we're looking at. So we have 1 liter of buffer that contains equal moles or equimolar concentrations of acetate and acetic acid, which, like we talked about previously, gives us a pH of 4.74. Now, to this buffer, so this would be our initial, to this buffer we are going to add 5 mils of 4 molar NaOH. 5 mils of 4 molar NaOH, right? So, what does it look like after, right? Which of these is the after scenario? Well, first let's think about what reacts, right? So we're adding a what? Correct, we are adding a base, which means we consume the acid, right? So we are going to consume this, right? And produce that, yes? So that means we should have less HX and more X minus. Does that make sense, right? In this particular scenario. All right, so let's go ahead and talk about how to solve a problem. So if we were adding strong acid or strong base to a buffer and we wanted a more quantitative relationship, right? First, we would add either our acid or our base, right? And because strong acid and strong base reacts completely, right? We would basically do a Rice or a stoichiometry calculation to come up with our new concentrations of HA and A minus, right? And then we would use a K expression to get everybody and then to get to pH, right? Note that this is the strategy when your strong acid or strong base is the limiting reactant, yes? As in the amount of strong acid or strong base added is less than the buffer capacity, right? Obviously, if it exceeds your buffer capacity, there is no equilibrium. There's nothing else to consider. All of it's neutralized, and the pH now is just dependent upon the excess strong acid or strong base. Yes, does that make sense? All right. So let's read a problem and do it. So it says, determine the pH of the original buffer described in sample blah after the addition of some acid, okay? So basically we would like to know, we're going to add some acid and we want to know the resulting concentration, okay? Now, let's talk about why this math is more thoughtful, okay? So what we're going to do, well, let's just solve it and then we'll do a comparison. So we have this many moles of that and this many moles of that in my water, right? And that's what we're adding our HCl to, right? So first, what I think is always helpful is let's go ahead and write down the weak acid hydrolysis that makes up my buffer, right? So we're going to start with our CH3 COOH plus H2O, and that gives us our hydronium and our A minus, okay? So, and then let's get our initials down there, right? And it says I have 0.3 moles of this, and I have 0.3 moles of this. And I do like to write down the moles so I don't forget that I'm working in moles right now and not molarity. And then it tells me that the pH of my buffer is 4.74, but we will worry about that later. And then it says I'm going to add 0.02 moles of HCl. I'm going to add 0.02 moles of acid. What gets consumed? And let's label these, right? So this is my weak acid, and this is the conjugate base, right? Protonated versus the deprotonated. If I'm going to add HCl, which version is that going to react with? Correct, right? So we are going to minus 0.02 moles here. We're going to add 0.02 moles here, right? Which means that now I have 0.32 moles and I have 0.28 moles over there, yes? And those are the new concentrations that we can go plug into our K expression, right? So we are talking about an acetate buffer, right? So I know that that Ka value is 1.8 times 10 to the negative fifth is equal to H3O plus times 0. It's in 1 liter, so 0.28 molar over my HA, which is 0.32 molar. And I could solve for my H3O plus and then subsequently solve for my pH. Yes? Alternatively, right, if you were so inclined, you could use the Henderson-Hasselbalch, right, which says your pH is equal to your pKa. pH is equal to pKa plus log of base over acid, right? And then you just need to bear in mind, right, this is your base, right? This is your acid. And make sure you do your pKa there, right? And that would work also. All right. Thank you for listening. Oh, and then the other point of reference is B, where you would be adding it to pure water, right? And so obviously all of it would dissociate, and you would get a very different pH change there, right? Than you get in your buffer, because the whole point of a buffer is the ability to neutralize. Yes? All right. Thank you for listening. Be good, and I will see you soon. Stay tuned for the next one.